My name is Francesco Pistis. I'm a PhD student from the National Center for Nuclear Research in Poland, under the supervision of Dr. Agnieszka Pollo. And today I will talk about the fundamental metallicity relation and its projection at high redshift, and a possible way to extend the study at higher redshift. I will give you an introduction about this relation and its evolution. I will describe the data used for the first results of my studies, the observed relation, and possible biases introduced by observation and data selection that can affect the shapes of this relation and mimic some kind of evolution. Then I will talk about further studies. So a galaxy can be seen as a system in communication with the gas in the intergalactic medium, and the metal poor gas can accrete into the galaxy, where it is used to form new stars. The stellar evolution then enriches the interstellar medium via supernova explosion and stellar winds. And then this enriched gas can leave the galaxy by wind outflow. The fundamental metallicity relation is a 3D relation between stellar mass, star formation rate, and the metallicity of star-forming galaxies. It is described for the first time by Manucci et al. 2010, studying Sloan data with high statistic at redshift around 0. They also compared this relation with data extracted from literature, and they didn't see any evolution of this relation up to redshift 2.5. The star formation rate dependence can be explained by the evaluation of metal poor gas by fall, and the stellar mass dependence can be explained by outflow and also aging model. Savaglio et al. 2005 studied 60 galaxies around with redshift between 0.4 and 1, and they found a shift of the mass metallicity relation, which is in agreement with the closest box model and with the downsizing model for galaxy formation. Lian and Marston 2010 studied the same relation and described a model including a time-dependent metal outflow or a time-dependent initial mass function, which described the evolution of this relation. They found a two-phase evolution with the mass metallicity relation evolving parallel to itself up to redshift 1.5, and then it started to flattening until today. In my studies, I'm using the bypass data, that is a spectroscopic sample with a redshift between 0.45 and 1.2, and a cross-matched catalog for Sloan data, with a catalog for magnitude, one for stellar masses, and one for emission line fluxes. The data for bypass are selected from the emission line and redshift flex that are the first measure on how well a line is measured, and the second on how much lines are used to estimate the redshift. We select star-forming galaxies with the PPT diagram using oxygen and H-beta lines, because nitrogen and sulfur are missing in the bypass spectra. We used the same star-forming selection for Sloan data, and then we followed the selection by Curti et al. 2010, applying a signal-to-noise cut on H alpha and H beta. Then we corrected the lines via Balmer decrement and Cardelli law. Then we excluded all galaxies with an high color excess. The first problem of this kind of studies is that different methods to estimate the feature can affect the shapes of the relation. For this reason, we choose to estimate the stellar masses from single stellar population model fitting using the model based on Brussels and Charlotte 2003. And the stellar masses are expressed with the initial mass function by Sabret et al. 2003. The star formation rate is estimated by oxygen lines, and Sloan data need a fiber correction. The metallicity has the problem to not have a unique method to measure it, but there are different calibration based on different available lines. We used 3 different methods based all of 3 on oxygen and H beta lines. And the following plots are all based on Tremont et al. 2004. In this plot are present triangle view of fundamental metallicity relation in the upper row, and the metallicity versus stellar mass, star formation rate, and specific star formation rate in the lower row. The 2 samples doesn't follow the same surface of FMR, but they are shifted in metallicity. And also in the 2D relation, we don't have a good agreement. So the question is, can this difference can be explained by biases introduced by observation or data selection? We studied 3 different biases on Sloan data that are the signal-to-noise cut on the emission lines used to compute metallicity, different a selection on the volume in the blue magnitude minus B star, that is the magnitude at which the luminosity function changes behavior, and different completeness of the sample, that is defined as the fraction of the blue galaxies kept in the final subsample. The effect of signal-to-noise cut is to reduce the explored surface of the FMR and the cut of high metal galaxies at the high stellar mass and low star formation rate. The selection magnitude is increase the inclination of fundamental metallicity relation, and the completeness effect is to reduce the surface to the central part. Then we compare vipers with the Sloan data with the application of the same signal-to-noise and volume B minus B star and completeness of vipers to reproduce the characteristic of the sample at high redshift. And The slant data with the biases is plotted in green. We still don't have agreement between the two samples. Another problem to the study of the evolution of the fundamental metallicity relation is the lack of spectroscopic data at the right redshift, passing through, from 10 to 5 in the local universe to tens of galaxies at redshift between 3 and 4. A solution could be the use of photometric data, which are simpler to obtain at high redshift. Another problem is the lack of metallicity calibration at high redshift. So a solution could be the luminosity metallicity correlation calibrated from the mass metallicity relation by Sanders et al. 2013. They applied, they introduced the color to reduce the dispersion around the mass luminosity relation. So the studies on the evolution of the fundamental metallicity relation need more data at right redshift. A solution is the use of photometric data, but we need to check and extend the calibration of the photometric metallicity at high redshift. A problem is that the mass metallicity relation and so the luminosity metallicity correlation evolves more than the fundamental metallicity relation. But with Sloan bypass and NEP wide field, we have enough data to cover a wide range of redshift. Thanks for your attention.
Thank you very much. There are a few questions on Slack. Maybe Tetsuya, you can just ask.
Okay, so I have one question. So you said that you use a different calibration method to derive metallicities. So how?
Yes.
It is known that there are systematics between different methods. So how did you solve this problem when you compare?
We are comparing the two samples with the same method of estimation of metallicity and to avoid any systematic difference.
Okay, you are using a single method when you compare.
Yes.
Okay, thank you very much. I have one comment. Actually, in my previous paper, I found a fourth parameter which is controlling the metallicity, that is surface density of stellar mass. So using SDS data, so this is very rosy galaxy. So it is very interesting to check this point for your higher redshift sample. So this is just a comment. Thank you very much.
Okay, thank you. I will check.
So Tomo asked whether your results at redshift 0.6 agrees with other work at the similar redshifts.
Other works at redshift around 0.6
Yes.
agree more with the Sloan data, but for example, Travaglia has only 60 galaxies, while in Vipers I have 1,000 of galaxies.
What about Jabran Zahid et al.? They had more galaxies, right?
Can you repeat, please?
Zahid et al.
I didn't understand.
Zahid et al. Paper,
Type the name in Slack.
redshift 0.8.
I know Wang et al. that are based on the always slant data, but at redshift 0.8, and they staggered the spectra. But they use different estimation of metallicity between the two samples.
So it doesn't agree? That's what you're saying?
They agree more than Vipers.
Okay.
So other papers, if I may intervene, some other work tend to show a similar flattening, similar tendency at Vipers, but broadly there are different results. Some agree with local measurements, some show some differences, but there are no other results at similar redshifts based on similar lines and with similarly large statistics.
Okay, thank you.
Thank you.
Okay, thank you very much. So let's thank Francesco again.